Good afternoon and welcome everyone to Specialty Chemicals magazine webinar with Arxada on making net zero a reality, sustainable solutions based on Arxada's chemical network. The need for sustainability has never been more urgent. Arxada is embracing smart approaches throughout their network to foster collaborative partnerships that will help in achieving net zero goals. Today, we have the privilege of being joined by three of Arxada's team who will share their insights on how we can collectively use these measures to create a thriving, environmentally resilient world. Please join me in welcoming Arxada's Senior Manager of Business Development, Marie Hoffmann, Head of Technical Evaluation and Development, Ulrich Mayerhöffer, and Technical Evaluation Manager, Philipp Kohler. Without further ado, over to the Arxada team.
Hello, everyone. Thank you very much for being here and joining us. I hope everyone can hear us well. Otherwise, there is a chat box, so please make yourself heard. We're very happy to be here today to discuss making net zero a reality. That's quite an exciting topic. If there is any question during the discussion, please drop them in the chat box. We will try our best to answer any question at the end. And also feel free to reach out. Here is my email address, so you can contact us after all in case a question are just coming a bit later. So welcome once again, and we're here to discuss making net zero a reality, sustainable solution based on Arxada chemical network. So today, high level, the topic will be about making net zero a reality. You know that already, but we will discuss PCF, so product carbon footprint, which is expressed in kg CO2 equivalent per kg product. This PCF has three scopes into it. So scope 1, which is linked to a direct emission, which is coming from a production facility. Our approach is to use specific technology to narrow this scope 1 emission down as much as possible. We will see that in a few minutes. In PCF, there is also scope 2. So it's emission coming from the energy that is used within the production facility in order to produce. Here we will see how our site in Visp is well equipped as we have access to low PCF energy sources. And finally, PCF is made of scope 3, where here we see emission coming from the raw material, the transport, and the packaging. And we will see as well today how our technologies, our specific process design, and sourcing strategy can help to reduce the scope 3 as well. So the discussion today will be split in 4 pieces. First, it will be a general introduction, just a few words about Arxada, so that you can have a think about or better understand who Arxada is. We will also do a short introduction about sustainability, just to make sure we're all on the same pages. We will then discuss the chemical networks that Arxada have access to in the Visp site and how this will be beneficial to making net zero a reality. In the third part, we will now narrow down the topic to reach this net zero. So how do we see it? What kind of solution we can provide to our customer to support the race toward better sustainable, toward reaching sustainable targets. And finally, out of the very theoretical discussion, we will see from this concept how it can be applied to reality, as we selected 2 use cases. The first one will be about niacin, and the second one about ketene and diketene. So hope you're excited, because we are. Let's start with a quick introduction about Arxada. So Arxada is somehow new, as per se, at least the name of it is new. You can see here, yes, somehow a new company created in 2021, but we actually exist since 125 years. So in a nutshell, we're the whole Lonza specialty ingredient. Lonza was created in 1909. You can see that on the slide. Over the time, a different company were acquired, but most importantly, in 2013, Lonza created the department called Lonza Specialty Ingredient, which a few years later, they decided to sell entirely. And we were bought as Arxada by a private equity and investor. And this is how the Arxada company was created. Since 2021, we launched our first sustainability report, and as of 2024, we're very happy to be in a position to support our customer to make net zero a reality. So just Global presence, how does that work for us? We are about 4,000 employees over the world. We have 14 R&D centers and 24 manufacturing sites. And all of this to serve over 100 countries around the world. We have 2 business units within Arxada. The first one is called Microbial Control Solution. So it's a lot of portfolio products. If you go on the Arxada website, you will be able to see that, where we develop solutions to fight microbes, really, on different type of materials. So, for example, we are active in home and personal care or in paint and coating. On the right side, you can see the other business unit, which is called Nutrition, Care and Environmental, also NCE. And this is actually where my colleague and myself belong. So we have 2 divisions where there is a lot of portfolio product, once again, nutrition and infrastructure and composite material. But today what we're going to discuss is CDMO solutions, which mean custom development and manufacturing organization for CDMO, where we do customized solution for your product. So in a nutshell, if the product you're looking for is not part of the Arxada portfolio, you can come to us and we will design specific solution for your need. So what do we do in CDMO? Which market do we tackle? It's quite broad. I must say we are well equipped to attack different type of markets. So we are active in nutrition, in personal care, in cosmetics, and a few others, as you can see here on the slide. So by definition, by heart, we are producers. So our main activity is to produce large-scale quantity of chemicals or of different types. So to reach this production large scale, but question can be where do we start? So there is different solution. We can start very small scale or just an idea in the lab, and we will bring this to lab, going through the different steps. First, the process development, then we optimize the process, we scale it up, we transfer, and then we start to produce. So it's really a concept from a few milligram or grams even to multi-metric ton of product. Of course, we're also capable of using a process that was developed already at large scale and is operating to, in this case, only, let's say, transfer and adapt in order to reach production. In addition to the production scheme you can see here, we also offer different type of services on demand. For example, we can support with analytical development in case the analytics are not developed within a project, or stability testing. We have all of this capability and knowledge at Arxada, and we're like super happy to bring that within a project when it is relevant for a project. So where does this CDMO project come from? We have 2 main sites operating 2 different specialties. The first one is about chemistry, so chemical asset. They are located in Switzerland, and this is what we're going to focus on today. But just for everyone in the room to know, we are also well equipped when it comes to biotechnology and precision fermentation processes, as we have a CDMO facility located in Czech Republic, where we operate and develop such process, as well as a few fermenters available for use in Rochester in the US. I will now give some time to my colleague Philipp to discuss a bit sustainability and introduce the concept. Thank you very much.
Thank you very much, Marie. So in the next few minutes, I would like to give you a bit of background what net zero is actually all about. Many of you will have heard of the concept. So net zero is related to the greenhouse gas emissions on a company level. So greenhouse gases, as we all know, are the major contributing factor to global warming. And many companies therefore set themselves goals to reduce the greenhouse gas emissions down to net zero. If you want to do that, you have to follow the guidelines set out by the Science Based Targets Initiative. That's an organization that defines those guidelines and also validates the targets once you have set them. The first step in this process is to select a base year. That's basically a reference point for the emissions. That should be no earlier than 2015. Starting from there, you have to define a first near-term target within 5 to 10 years of the base year. And the emissions in that year should then be in line with the goals of the Paris Agreement. So trying to limit the global warming to 1.5 degrees Celsius. Then next, you set yourself a long-term target, which should be by 2050 at the latest. In this goal, you reduce your emissions down to a residual level, which means down to less than 10% of the base year. But you're not finished there. You have then to compensate the residual emissions, which you cannot avoid by any other means, through other measures, for example, carbon capture, reforestation, or carbon credits. Now, I'm sure many of you have your own goals on your company level to reach net zero. In fact, when you look at the 2,000 largest companies worldwide, you see that more than half of them have already set themselves net zero targets. However, only 2% at the top have achieved the targets, and none of those are chemical companies. So we see this as a major challenge to reach those goals together, and we want to show you how Arxada can be a valuable partner to reach your sustainability goals together. In order to quantify the emissions, you have to break it down to an individual product level, and for that you can determine the product carbon footprint. So the different stages in the life cycle of a product are depicted here in schematic form. It starts with the procurement of raw materials on the left. Those can be coming from minerals, so from mining, from biosources, for example, or very importantly, they can be raw materials that were produced by another company and delivered to you. Then there's a transportation stage, of course, where the material is transported to the manufacturing site, so your factory essentially, and there it is converted into the product. This step also requires energy input. Then the product is distributed to the end user, where it undergoes a use stage. And then it reaches end of life, it goes to waste, or in some cases also recycling is involved. Throughout all of these stages, there are certain emissions of greenhouse gases associated with the stages. And now in order to quantify them, you have to find a common source. So not all gases are the same. The most prominent one is carbon dioxide, but there are also others such as methane or nitrous oxide. And in order to have a fair comparison, we then apply a factor to normalize the output in the form of CO2 equivalents. So we can state your kilograms of CO2 equivalent per kilogram of product, for example. A few more definitions. Emissions associated with manufacturing are called Scope 1. Emissions associated with energy production are called Scope 2. And all the rest is then summed up as Scope 3, which can be either upstream or downstream of the manufacturing step. Now, in order to express your PCF, you can stop at the finished product as soon as it leaves the gates of your factory. That approach is called cradle to gate. Alternatively, you can also include the use and end of life phases. In that case, you call it cradle to grave or cradle to cradle if recycling is involved. That is not to say that cradle to grave is always better than cradle to gate, because in many instances, especially in the chemical industry, you do not actually know what the product is used for, or you do not, or one product can have multiple uses. There is also another point which is important to consider now. Take, for example, the situation where Arxada produces a product for you. So we produce this in our manufacturing site and then deliver it for you for further conversion into your own product. So from your perspective, the PCF that we give to you for our material ends up as Scope 3 for you. This is especially important in the chemical sector because on average more than 2/3 of a company's greenhouse gas emission is linked to Scope 3 emissions. So in order to reduce your own greenhouse gas output, you have to control your Scope 3 output. And Arxada can be a valuable partner for you to reach that, because we can produce our products with a low PCF, and therefore we can help you to achieve your own goals. Our Scope 1, 2, and 3 is Scope 3 from your perspective. So we can reduce our output by different means. For the raw materials, we can use our supplier network, our trusted partners who can also deliver low PCF raw materials to our site. Then for the energy, we can use low carbon footprint energy sources such as hydroelectric. And for manufacturing, we can use our technologies. That means we can do process development with our R&D department, but also importantly, we can use our unique asset, our chemical network. And this is the next part of our presentation. With this, I would like to hand back.
Thank you, Philipp. So speaking of chemical network, we're now going to try to explain a bit how we see it and what it means at Arxada Visp. So I already gave you some hints. Where is the chemical network located? Well, it's on our Visp site. So Visp is a small city or village, I guess it depends who you ask, in the south of Switzerland, very close to the border with Italy. And this is where our largest production site at Arxada is located, but also the heart of our CDMO project when it comes to chemistry. So here is a very nice picture, at least we like it very much. You can see mainly the site here. We are located in the middle of the mountain in Central Europe, and we will try to highlight some of the assets that we have available on site that might be very relevant to reach net zero. So first, we have something that is called the AGU, which is basically a steam cracker as well. And from there, we produce various small molecular reagents, depending how you look at it, such as ethylene, acetylene, CO, methane, and hydrogen. We also have available on site the air separation unit, or ASU, where we can extract and make use of N2 and O2. In addition, we have the ammonia plant, so we will be able to produce our own ammonia from the Visp site. We also have a cyanide plant. From there, we can produce and make use of HCM. We have a ketene and diketene production plant. We will see toward the end of this presentation how we can make use of it. We have an anhydride plant where we can produce acetic anhydride as well. Finally, we have a few multi-purpose assets, and this is exactly where we're going to make on-demand projects. So specific technology, we can use various types of chemistry. You have one project, one compound, we can make it on demand through this multi-purpose asset. And of course, none of this would be possible without R&D team developing and making sure we can produce, so we have this capability on site. Now we can see how the AGU and the production of ethylene, acetylene, CO, methane, and H2, how it works, and later on a bit how that can be used to reach net zero targets. All right, so what is the AGU? Well, the AGU, we fuel it, if you will, we feed it, with naphtha. We could also use LPG, and out of the AGU, as already mentioned, we can produce various small molecules. You can see that on the screen. Then what do we do with it? Well, there is further utility on site. So for example, we can produce then ammonia or HCN or chlorocyanides. But what does it mean and how do we use them? Well, we have a lot of different streams and a lot of different technologies. So it's a lot of chemicals on the slide. So sorry for whoever is not a chemist in the room, but you can see there, what you can see there is that thanks to the variety of technology and available equipment, we can do different type of chemistry, which means with this very small molecule, we can access a lot of different structures. And that's, I guess, the massive takeaway for today. In addition, let's have a look at the ketene and diketene plant we just mentioned. So in this case, we feed the plant with acetic acid, which is then cracked to obtain ketene and diketene. And those two very small molecules are very, very reactive. So we can further react them with various reagents, once again, to create different type of structure. So here on this screen, you see some molecules who are final products. You can see them from the Arxada portfolio if you go on our website. So what do we do with all of them? Well, as mentioned, some of them are portfolio products, but as we're here discussing CDMO, what we need to see here is that any of these small molecule or more advanced intermediates that we make on site and have access to, they can be redirected to the CDMO assets, to the multi-purpose assets, to be of use for a very specific project, for your project. And now I'm going to hand over to my colleague, and he will dig a bit deeper to explain how, thanks to all this utility and technology, we can actually reach net zero.
Yeah. Thanks, Marie, and hello, everybody from my side. And bear with me for the next couple of minutes. As you may have already realized, our chemical network is quite complex and quite difficult, so we try to walk you through it in the next couple of minutes through the most important parts and steps and connections within that network. The heart of our network, as Marie already mentioned, is our steam cracker, our HEU. That HEU is fueled from naphtha or LPG, and it's also using oxygen from our air separation units. In addition, to run the plants, we also need some energies like electricity. The output of the HEU, it's methane, which we are mainly using in our HCN plant to produce HCN. We have acetylene, which is converted in our dedicated asset to our Arxada portfolio products. And we also have the connection from all our network streams into our multi-purpose assets on site, where we create customized solutions for our customers. Within our multi-purpose assets, we offer 5 highly flexible and interconnected chemical multi-purpose complexes, which houses a total of 22 independent plants. We have a large variety of different materials of construction, like cast alloy, glass-lined reactors, and stainless steel, with a total installed reactor volume of about 670 cubic meters on site in this. The next important outlet of our cracker is hydrogen. It can also be used in our multi-purpose asset. The majority is converted to ammonia. And finally, we have the ethylene, which is mainly used in our acetaldehyde plant on site. All that production of the cracker is related with a certain amount of carbon emissions, which give already a not negligible CO2 footprint to our production on site. If you now go further in the chemical network downstream, we can look at our ammonia plant. There we are again using nitrogen out of our ASU plant to produce ammonia together with the hydrogen. And we have to add some steam out of our steam power plant. The used ammonia is then again used in our multi-purpose assets, or together with the methane converted to HCN in our HCN plant. The HCN that we are producing, again, can be used in our multi-purpose asset, or it's converted in our chlorocyanide plant into chlorocyanide, which will then be further converted into our products we sell to our customers. Finally, the acetaldehyde is converted again with ammonia to methyl ethyl pyridine, which is a key building block in our niacin production, which will play a vital role in the later part of our webinar. And the second very important network on our site is, as mentioned before, our ketene and diketene network. There we are using acetic acid as the major fuel to run those the chemistry there and create ketene and diketene. Ketene and diketene, we can also directly use it in our multi-purpose assets, but quite a large amount goes into our acetic anhydride plant, which is then converting it to acetic anhydride. All that operation, to create then the final products, we need product-specific raw materials, which we source on the market. And we are creating certain amounts of solid and organic waste, which we incinerate in our attached infrastructure on site in Visp. And we have some aqueous waste, which we are treating on the connected wastewater treatment plant in Visp. All those operations also come with a certain carbon footprint, which is adding up to our PCF of the overall production. And what we finally get out is our product portfolio and our customized products we are selling to our customer. Now, to make all that complex network net zero requires a certain amount of effort and steps. We narrowed it down in 3 major steps. The first one is tackling our energies. There we are trying to switch to low carbon energies. The first step is to move electricity to low PCF electricity. It can either be renewable energy like solar power or hydro power, which we, thanks to our location in the Swiss Alps, have plenty of, but it could also incorporate nuclear energy. Depends on the mix that's required for our production. The next major energy source we have on site is then our steam plant. It's both run by our organic waste on site, and the energy is coming out of its incineration, or we fuel it by natural gas. So to make our steam net zero or low PCF, we have the options to switch from natural gas to biogas. The second alternative we have is to switching to electrical fueled steam boilers to use renewable and low carbon energy to generate our steam. That will allow us to create or make our whole energy supply net zero, and also the downstream value streams out of those assets which are just run with energy like our ASU will then become net zero. Then to go one step further, the major part to achieve really a low PCF or our net zero targets is to tackle our feedstock. And there we have to switch to renewable feedstocks. What you see on that slide on top is the conventional setup, like a classical cracker is normally run. In our case, we are fueling our cracker with fossil naphtha. There then all carbon atoms in the naphtha will be brown. They will be cracked in the cracker. There are process emissions related to the operation of the cracker, and we will end up with small molecules, which we will further convert in our chemical network, which is also exhibiting some indirect carbon emissions due to yield losses in the processes or direct emissions of the processes and our products. We can now offer two options to make our feedstock green. The one is quite simple. It would be just switching to 100% green feedstock. There we can use green naphtha in our cracker. That would also mean that all carbons we are entering in the cracker will be green or coming from renewable sources. There is also our related process emissions of the cracker, and all carbons within our small molecules coming out of the cracker will be green, meaning that we can also make our indirect and direct process emissions of our chemical network to be green. In addition, our downstream molecules will incorporate green carbon atoms. The second option, and in most cases, that's our favorite option and also the most cost-efficient option to come to a net zero product, is the mass balance approach. What does it mean? So we use a mix of brown or fossil naphtha and green naphtha to fuel our cracker. So we will end up with a mixture of both brown and green carbon atoms, which will then give us enough green carbon molecules in our downstream streams to make our cracker emissions and also our process emissions and indirect process emissions of yield losses green. Important in that case is that the small molecule carbons will remain brown carbons. So how does that now look like for our chemical network? It means we are feeding our cracker with a mixture of naphtha, LPG, and green naphtha. That will make our process emissions of the cracker green, and it will also incorporate enough green carbons in our downstream outlets to finally offset all downstream related emissions to become green. The same concept we can apply for our ketene and diketene network by adding bioacetic acids into the mixture of our feeds. That will give us enough green ketene or green diketene molecules to make that downstream chemistry green as well. And finally, it will allow us to offset the emissions related to the production of the downstream chemistry and the waste. So the remaining part or the remaining contribution we now have for our PCF contribution is now coming from our scope 3 and product-specific raw materials. To tackle that scope, we established close collaborations to our sourcing partners to offer us special low PCF qualities and raw materials, which then allow us to use the lowest possible PCF also in our source raw materials to give you finally a net zero product. As we learned before, net zero just means it's a 90% CO2 reduction. So what can we do with the remaining 10% of carbon emissions in our productions? And they're already established on our side on this. We have the possibility to capture CO2. We can capture it either as CO2 directly from the off gas of our cracker and transforming it into liquid CO2, or we can capture it as carbon monoxide, which is a bit more complicated, but it's also avoiding CO2 emissions. And both streams can be used in our multi-purpose assets to convert it into chemistry. Or as we also collaborate with partners and companies which store it for us, there we can either offer to incorporate the CO2 we are capturing into demolished concrete from construction to produce recycled concrete. And we can also offer permanent storage underground. So to make it a bit more tangible, what that would mean, we selected two use cases out of our site in Visp. The first one is our niacin. That's quite a legacy product for us, which we are producing for several decades now. The synthesis starts with the ethylene we are getting out of our cracker. It's converted with oxygen and oxidation reaction to acetaldehyde, which is converted to paraldehyde, which is converted with ammonia out of our chemical network into methyl ethylpyridine, which is then finally converted with nitric acid into niacin. That last reaction is producing direct emissions, as it produces also CO2 in the chemical reaction, and it produces a certain amount of nitrous gases, which we recover to bring it back into our nitric acid synthesis. Now, to get that process net zero, we are playing the same mass balance strategy. We are feeding our cracker with a certain amount of green naphtha, which is mass balance wide enough to offset the direct process emissions from our cracker and to have enough green carbons in the ethylene to cope for the indirect carbon emissions we have due to yield losses in our chemical network, and finally for the direct process emission and indirect process emission of our niacin plant. That allows us in the end to end up with a net zero niacin quality. So here again, you see the related dedicated assets in our chemical network that we are using to make our niacin. So again, how does our route towards net zero niacin look like? We are starting to add green electricity. We are therefore using renewable electricity. We are making our steam green by turning it by electrification. So we are using electrical boilers to produce our steam. And then we are starting to offset each process-related carbon emission by adding a certain amount of green naphtha. The first step would be to offset the direct carbon emissions from our cracker related to the ethylene and the hydrogen production. The second step would be to offset the indirect carbon emissions related to our operations in the chemical network towards our niacin plant. The third step would be to offset our indirect carbon emissions of the niacin. That would give us then also the green waste. And finally, the last portion of green niacin we are adding mass balance wise to our cracker will reduce the direct CO2 emissions of the niacin process. In the end, the result is a net zero niacin quality. And with that, I'm handing over to Philipp, which talks a bit about our ketene offerings.
Thank you very much. So you've heard about niacin, which you could call an in-house example. I will now show you an example of a more customized solution, where especially our R&D team had a major influence in making a more carbon neutral process. And for that, we will again leverage our chemical network. In this case, the ketene stream. So our target was this aryl ketone here, which should be made through Grignard chemistry. So starting from the Grignard reagent on the left, that would react with acetyl chloride. And traditionally, this process runs smoothly in the presence of a catalytic amount of copper chloride to give the desired compound in 94% yield. Along with it come some magnesium salts and also a few side products, such as the dimerization product shown at the bottom here. Now, this approach has some downsides. First of all, the production of magnesium metal comes with a high carbon footprint, more than 20 kilograms of CO2 equivalents per kilogram of magnesium. And this goes completely to waste, if you will, because the magnesium salts that come out of the process cannot be recycled. They have to be used as waste because they are contaminated with copper. Similarly, the wastewater coming out of the process is contaminated with copper, which necessitates a very extensive wastewater treatment to lower the copper levels down before you can release the wastewater back into the environment. So our R&D department tackled the problem at the root and got rid of the copper catalyst in the following way. So they proposed to replace acetyl chloride with carboxylic acid anhydride. Now, this choice seems obvious, but in fact it's not obvious when you look at the literature, because most examples of Grignard reactions with carboxylic anhydrides employ cryogenic temperatures and give only moderate yields with large quantities of side products. However, we found that under the right conditions, around 0 degrees, the reaction proceeds very smoothly with almost no side products, even in the absence of copper. So copper is no longer needed, and therefore this problem can be avoided. We did not want to stop there because we still have a potential waste stream with this magnesium carboxylate here. So we can treat this with a mineral acid to generate an inorganic magnesium salt. And this is now not, there is no copper contamination present anymore. Therefore, the magnesium salts can be isolated and actually sold as a secondary value stream. It has different applications, for example, for alloys, performance materials, or in the agrochemical industry. And to make the process fully cyclic, we wanted to recycle the carboxylic acid. And for that, we made use of the network. Now comes the ketene stream. So ketene regenerates the carboxylic acid anhydrides. And at the same time, acetic acid is produced, which we can feed back into the ketene generator. The water produced in this process can be used for steam production. So in total, this closed value cycle produces the desired compound and the secondary compound with almost zero waste output. This is very good for the carbon footprint as well, because you can imagine that every carbon ending up in the waste will end up as carbon dioxide equivalents. So if we can avoid that much waste, we can really lower our PCF. To lower it even further, we can make use of the same strategy as before. So we can use a biosource of acetic acid, and we can use energy sources with a low carbon emission. In order to quantify the amount of waste generated, we wanted to bring in a new green metric, and for that we proposed this here, which we term atom efficiency. Now, first of all, please do not confuse this with atom economy. You may know atom economy, which was introduced by Barry Trost, which is a different concept on a more theoretical level. So it considers the theoretical balance of a chemical equation. However, we want to focus more on the real life situation. So the definition is shown here. Atom efficiency, it's quite simple actually. It's essentially the molecular weight of the product divided by the molecular weights of the input streams. And for that we consider all input streams, raw materials, reagents, catalysts, solvents, etc., anything you can think of. And then we just apply correction factors for the chemical yield and for the recycling rate. So for the theoretical example at the bottom, you may, for example, consider that the solvent is fully recycled, so it will completely drop out of the equation. Then the atom efficiency is the molecular weight of the product divided by the molecular weight of the two raw materials and the reagent. I mean the raw material plus the reagent. Now in our real example, the Grignard reaction, we can also calculate the atom efficiency, and in the traditional, under the traditional conditions using copper, we can see that the atom efficiency is moderate in the 50 to 60% range because so much waste is generated. So you can run this process using either acetyl chloride or acetic anhydride. However, in contrast with that, our new process without copper, the fully closed value cycle, delivers very high atom efficiencies, which are in fact only limited by the chemical yield. The other contributing factors such as solvents and recovery of reagents are not really an issue because we can reach really high recycling rates of solvents and reagents in practice. So you have seen in this example how we can lower the PCF by really minimizing the waste output of a given process. And with that, I would like to hand back again to my colleague for the conclusion.
All right, thank you very much, guys. So I don't know if you can still see me. Some people are saying my screen is black. So anyway, you can hear me. So just to conclude and summarize, hope you're still with us. So we're very happy today to discuss the WISP network and how it is ideally positioned to potentiate net zero journey. We really see the power of our concept to reach net zero, and nowadays sustainability is key, right? So let's do that together. When it comes to PCF, the option that we see and discuss today is how to reduce scope 1. Once again, scope 1 means direct emission from production. And within WISP, we have the possibility to reduce this to zero via the use of green feedstock, such as green naphtha and biogas. When it comes to scope 1, we will include technology or make use of technologies such as the AGU, production of H2, CO2, you name it. We can also make use of the ASU in the ammonia plant or ketene and diketene, all of the good stuff we discussed today. Regarding scope 2, this is about the emission from the energy sources, and we feel very fortunate in WISP to have access already to this low PCF electricity that we discussed over the last 44 minutes. In addition, we will be able to reduce the PCF contribution of the steam to zero, thanks to the use of biogas and electricity. Last but not least, what do we do about scope 3? So here we have different options. So first, as discussed, we have this vertical integration, which means that instead of buying an intermediate, we could likely go backwards in this chain and produce this intermediate ourselves, which means we don't need to buy that raw material or intermediate from the market, but we can produce it, and we can produce it with a low PCF. We will also, of course, collaborate strongly on a very global level with a different partner we have. So as mentioned, we exist since 125 years. We have 24 production sites. So as you can imagine, we have a very large network of supply already. And now we're engaging more and more into defining which supplier will be the best for us to work with when it comes to low PCF raw material. Finally, there is a real effort coming from the development team. Hopefully you saw that from the discussion with my colleague Philipp, because we are trying to develop the best process design in order to reach a low PCF. And this will, for example, go with recycling of some of the raw material, which means we need to buy less raw material, which means that is reducing the scope 3. But we have many other ideas, and we hope that you will reach out to us so that we can discuss further and eventually try to see how that works for you. So in terms of PCF, where are we at altogether? Scope 1, with offsetting, we can reduce to zero. Scope 2, low energy electricities, low PCF, energies, including electricity and steam, we can reduce to 0. And scope 3 is to be defined, but we have a few solutions how to lower it as much as possible. So thank you very much for your time today. We hope you've seen the potential that we're seeing on how to make net zero a reality. We are very ready to support you, your project, and find the best solution for the world, I would say, because sustainability is a general topic, not only a chemical topic. So please do reach out to us at any point. We would be very happy to try to find the best solution. Here you see an email address, so myproject@arxada.com. Otherwise, you can find us on LinkedIn, for example. You have my email address, and for sure, there is a very nice Q&A section in this webinar. So feel free to use it, and we will now try to address the questions that were raised during this discussion. So thank you for your time, and we are opening for the question. We might stop sharing, and I will. So I still don't know if you see me, but it's not needed. So a few questions around naphtha I can see in the chatter. So naphtha and fossil naphtha, green naphtha. So I will address that one to my colleague Uli. So one of the questions I will just say them, what is the premium to use green naphtha instead of fossil naphtha? But overall, maybe Uli, you could comment on the availability of such material and what it means in terms of price, generally speaking.
Yeah, so the price question is one we are quite often asked, so thanks for that. But currently the premium we are paying for green naphtha is about 3 to 4 times the price of brown naphtha. But the source of our green naphtha is coming from sustainable airline fuels, which we think and all forecasters are suggesting that it's an exponentially growing market, also due to the regulations enforced within the European Union. So the prices are expected to come down, and we think that the price premium we will see in, let's say, the medium time frame up to 2030 is about twice the price of brown naphtha.
Thanks, Uli. I think one more in the chat around the same topic. So is the composition of green naphtha sufficient for cracking to ethylene, acetylene, CO, methane, and H2? Can you really exchange fossil naphtha with 100% green naphtha, or do you have to mass balance?
So the short answer is yes, we can replace 100%. The other question is if it makes sense. So for example, SBTA regulations do not account for any carbo or green carbons in our final products. So there's actually no need to reach net zero or no benefit if you would use 100% green naphtha for the production in our cracker.
So really it's about, if I may elaborate, it's about what is the need exactly, right? Some customer will want to have such green carbon within the product, doable. Let's switch 100% to green naphtha. But for some others, when it's reaching the net zero targets, this green carbon, they don't need to be within the product, right? It's just a related emission that need to be controlled. In this case, mass balance might be a better approach, simply due to the fact that economically, if a bit less green naphtha will be beneficial on the product. But we are happy to do both. It's all about making sure we understand what you're after and what's important to you, and we will find a solution. So I can see also a question, which is, can I get today's PowerPoint? Absolutely. Please, Brian, reach out to my project or my own email address, Hoffmann@arxada.com, and I will be happy to connect and share the slide with you. Few other questions. So maybe that one for Uli or Philipp, are you able to calculate PCF for CDMO customer products? Whoever wants that.
Well, I may take this one. So yes, we will be able. So we used to external sources to help us to calculate our first PCFs at the moment, but we are building up that capability internally. And our NC CDMO resource is sitting next to me. That's Philipp, that will do the PCF calculations in the near future.
Thanks, Uli. Speaking of Philipp, Maybe Philipp, can you tell us if it is possible to reduce emission by buying carbon credits?
Yes, Marie, thanks. That's a very good question, actually, and a controversial question because carbon credits are the source of some controversy. So up to recently, my answer would have been no, you are not allowed to reduce your emissions to reach net zero. You're only allowed to use carbon credits to offset the residual emissions. If you remember, you have to reach less than 10% of the original emissions, and the remaining amount you have to compensate. So for that, you can use carbon credits according to SBTi. But now the situation is, since April, I believe, SBTi released a statement that they will allow carbon credits in the future to offset scope 3 emissions as well. That led to some controversy, also from the employees of SBTi directly, and also from outside. So it's, I think, something we have to follow. We have to follow this development in the future, how it goes, what will come out of it, and of course, Arxada will follow all regulatory changes in the calculation of PCF and of net zero very closely in the future to be of use to you.
Thanks, Philipp. Maybe we can take a couple more. Thank you, everyone, for making this a dynamic session. And with a question, feel free once again to add additional question. And whoever we cannot answer, we will make sure to reach out to you directly later on to answer the question. So an interesting one, I think, is what would be the source of biogas used to unlock the low PCF of the steam? Maybe for you, Philipp?
Biogas, yes. So there's the Swiss natural gas pipeline, I believe it's called. We are connected to that. So normally this is also used for heating, but we can get that at Arxada FISP also. So we can get biogas from that pipeline. There is also here a bit of a problem with legislation, I would say. So I understand that there is no official or international regulation to declare biogas. So it's on a per country basis, let's say. And in Switzerland, only Swiss sources of biogas are actually acknowledged. So if we want to use biogas at the moment, it still has to come from Switzerland. However, there should be a European regulation in the near future, I think next year or so. And hopefully that will then expand our scope so we can get biogas also from European sources, and that will make larger quantities directly available to us. I hope that answers the question.
I think it does. Hopefully the people will think the same. But I believe what we're also seeing in this answer is this is a very dynamic topic, right? I mean, it's somehow new and the rules are evolving and they will continue to evolve. That's absolutely normal. And I think it's for the better. So we're following that on a daily basis. Our team is strongly connected to every information to make sure we're doing the right thing when we calculate and getting the right option. But to stay at the forefront of this sustainability topic, we for sure all have to work together and make sure we have some sort of uniform rule around Europe and hopefully very soon around the world, but we're ready to make that happen. Another question here, probably for you, Philipp. What methodology are you using to calculate your own PCF? TFS, so Together for Sustainability, seem to become the standard in the industry. Is that something you're using as well?
Yes, thank you for this good question. You're definitely right that TFS is becoming the standard and we are using this. I would say it depends always what the customer needs. So it depends on you, what you need for your own calculation. So we can, of course, adapt to other methodologies if that is required. But TFS seems to be the major thing at the moment, or becoming the new standard.
Thank you for that, Philipp. So yeah, here again, very, very dynamic environment, also depending on which country, of which guideline and regulation you wish to follow, different type of rules will apply. So we have our, let's say, standard way to do it, following the rules most of us know about. But if something specific is needed because of a country, because of a market. We're also happy to make that happen and to take that into consideration, right? What we develop is customized solution, not only about the product, but it also goes alongside everything for the product. So I think we're going to close this session today. Thank you very much, everyone who attended. Please reach out if you want to follow up with a discussion on the topic. If you see that as a powerful initiative for your own project, I think we all do, right? Which net zero is not only a chemical industry topic, but we're all looking into solutions. So very happy to support. Do reach out. I will just drop my head here because I heard I was like a black camera for a few. So I'm a real person and they are too. Those are my great colleagues. Thank you so much for today's call. And we're looking forward to supporting your journey towards net zero. Thank you.
Thank you. Thank
Bye.
you.